Now, what about limits that don't exist? In Calc 1, we had a version of this. So in Calc 1, if you remember, we would have some kind of function, and we would approach some value a. And when we did that, we would have it, here's m, here's n, and we would hop to a new point and have the function continue on, right? So this was called a jump discontinuity. At x equals a, if you remember what those were called. All right, so what's happening is that the limit as x approaches a from the negative side of this function was m, and the limit as x approaches a from the positive side was n, right? N is in Nancy. So m is in Mary. And so since these are different values, that from the left and the right, that proved that the limit did not exist. Does not exist. DNE. Okay, what are we going to do in Calc 3? So how can we kind of keep this alive? So we have some kind of, surface or something. And we want to approach a point x, y, and we want to figure out whether or not it exists. So what we're going to have to do is we're going to have to find ways to approach, just like we did here. See, when you approach in Calc 1, you can only approach from the left, right? So there's the left one, and the right. And that's it, right? So there's only left and right because it's, all in one variable. But in Calc 3, that's not the case. So what we're going to have to do is we're going to have to find more than one way to approach the point, right? Because we don't just have these two ways, left and right. So we have to find two ways. Sometimes they'll be left and right, but sometimes there'll be other things to approach the point xy that yield different limits or different limit values. And that will prove, just like it did in Calc 1, that the limit does not exist. So you're going to approach from this direction, and then you're going to approach from this direction, right? So you can come in from different ways, or you could approach from up here and head that direction. So you have to find some different ways to approach the line, and it won't be as straightforward as it was here, right? Where you approached x equals a from this way and x equals a from this way, right? It won't be like that. So it'll be more complicated. All right, so let's see one, shall we? This is confusing. So let's show that each of the following limits fails to exist by demonstrating that you can get different limits on two different paths. And the hard part about these is finding the paths. All right, so domain. Just for starters, we remember that we cannot divide by 0, so 3x plus 2y cannot be 0. And if I wanted to solve this, this would be 2y cannot be negative 3x, which would mean y cannot be negative 3 halves x. I'm just drawing it that way because I want to know how to put it on my paper. All right, so negative 3 halves x is like this. Right? Okay, so there's negative 3 halves x. So y equals negative 3 halves x. It goes through the origin, which unfortunately for us is the point we're trying to do. So we know the domain is all of this to the right of that line, all of this to the left of that line. Yes, you do have to draw that. And then you find the origin right here. 0, 0 is a boundary point. Okay. So we have to find ways to approach that boundary point of 0, 0. Because just sticking in 0, 0 is not going to work. 0 over 0 would make, right, 0 goes in here, 0 goes in here, makes 0 over 0, which is indeterminate. And where there is no L'Hopital's rule, so that isn't going to work. So we need to try some paths. Okay, the easiest paths to start with are the x and y axis, right? So if I approached from the x-axis like this, let's talk about that. So path 1, let's approach from the x-axis, which of course is y equals 0. All right, so what would happen to our limit? If we do that, the limit as xy approaches 0, 0, well, let me put it this way. If I put 0 in here, there's no more y, right? So I'm actually going to change this. It's no longer going to be xy. It's just going to be x because there won't be a y anymore because y is turning into 0. So x approaches 0 of 4x minus 0 over 3x plus 0, right? Technically it's 2 times 0, but that's 0, right? So this is the limit as x approaches 0 of 4x over 3x. And you might think, oh, that's a problem. No, it's not, right? Because the x's will cancel, right, and be gone, and it leaves you with 4/3. Right? Our algebra is still true. So this is approaching 4/3. That's the limit. Now I just need another path that will go to a different number and will be great. Well, the other easiest path besides the x-axis is the y-axis. So what if I approach down the y-axis like this, heading towards the origin, right? Okay, so let's take path number 2, the y-axis, which is x equals 0. All right, so when I put that in, there won't be an x anymore. So it'll be the limit as y goes to 0 of 4 times 0 minus y over 3 times 0 plus 2y, which is the limit as y goes to 0 of negative y over 2y, which is negative 1/2, because the y's disappear. And those are not the same number. I'm essentially doing the same thing I did in Calc 1. I found 2 different numbers, therefore the limit does not exist. There, and I just wrote that up, right? It's a contradiction, right? 4/3 is not equal to negative 1/2, therefore there is no limit, and we are done. Now, if we want to look at this in Maple, I think I drew it. Oh, I showed how to find the limits right there. That's how to find them with Maple. Of course, you're going to have to do them by hand, and notice they came to different values, and you can see, oh, it's kind of a mess, right? And it's giving me those jagged lines because it's all over the place. So that's to be expected. And interestingly enough, Maple does tell us when it's an undefined limit like this. So it's letting us know. So that's one way to check yourself when you have to do these problems for an exam. All right, so let's do part B. We want to find the limit as x goes to the origin again. The origin's really common for us because the origin creates a lot of problems, right? Division by 0, logarithms of 0, things like that. Okay, so we want this to go to 0, so we have to look at our domain. The domain is actually pretty easy because 3x squared plus y squared cannot be 0. The only way that's going to happen is if xy is 0, right? So therefore, it's same as the last one. We have a graph, we have the origin. Well, it's not the same because there's a boundary line on the other one, but it's the same idea. Okay, so I can have anything except that point. Oh, that point creates problems. Okay, so definitely 0 is a boundary point. We can just make a note of it. It's the only boundary point there is, so it's definitely obvious that it's a boundary point. So we need some paths. Okay, so let's do it. So path 1, I mean, we can try the same path we tried last time. We can try the x-axis. So I can approach from the x-axis. I'll write it up here. Path 1, which is the x-axis, which is y equals 0. Okay, so Once I put 0 in here, there won't be any more y's. So the limit, it'll be of just x going to 0 of 4 times x times 0 over 3x squared plus 0 squared, which is the limit as x goes to 0 of 0 over 3x squared. And that's 0, right? So now we don't actually have to go all the way to 0 over 0, which technically is indeterminate, but you can tell it's 0 all along, right? So what's going to happen is it's 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, all the way into that origin. So the limit is 0. It doesn't actually matter what the actual point value is, right? What matters is that it was 0 all the way along going into it, right? As I plow through this entire x-axis, it's 0 every step of the way. So that is 0. Okay, well, just like the last one, we could try the y-axis. Okay, so it's not going to work, but I want to show you guys what happens when you try it. So if you try the y-axis, path to the y-axis, which is x equals 0, you can perhaps see the problem you're in. It's 4 times 0 times y over 3 times 0 squared plus y squared. That's 0 on the top. So 0 over y squared. And again, that's 0 all the way. Literally every single point, it's 0. So the limit is just 0. That's not good, right? So we didn't prove the contradiction. I need them to have a contradiction, and we're not having it. So the x and y axis isn't going to work. I need some other path. And this is where it gets fun, because you can try all sorts of paths. There's lots of ways to go. You can try parabolas that go through, like y equals x squared. You could try, all sorts of things. I'm actually going to try a diagonal line, right? The diagonal line, which is y equals x. So let's see how that goes. All right, so path 3. Diagonal line y equals x. It's not the only way we could go, but it's going to be nice and easy because the algebra will be simple. You also want to look ahead a little bit and think about what's going to happen here. So if I let y be x, then once I substitute, there won't be any more y's, right? It'll be the limit as x goes to 0 of 4x times x over 3x squared plus x squared. Or you could have reversed this and done it x equals y. It doesn't really make any difference. So that's the limit as x goes to 0 of 4x squared over 3x squared plus another x squared is 4x squared, which is 1, right? That's the limit as x goes to 0 of 1, because this whole thing divides away to 1, right? So that's 1, and there we have our contradiction, because 0 is not equal to 1. All right, so let's put these together. Right? Contradiction. 0 is not equal to 1. Therefore, the limit does not exist, and we've proven it. All right, I'm going to go along and finish this problem. So we want the limit as xy approaches 0, 0. This is x squared plus y to the 4th in the denominator. So it's still going to give us the same issues, though. If the domain, we can't have division by 0. The only way that's going to happen is if xy is 0, 0. So you can't have the origin yet again. It's a pretty classic problem. Oh, I never showed you the maple from the previous one. Hold on one second. So you can see, look at the ridge lines. See? So if I approach on the diagonal line, it's 1. But if I approach from the x and the y axis, it's 0. So it's this weird fold of a paper. And so as I shoot along the x-axis, it's always 0. But if which is right in the middle there, right? There's the or the y-axis right there. So, no, sorry, x-axis, my bad. X-axis. I got disoriented there. So there's the x-axis, right? And it's always 0 all the way along. But if you come up on this top ridge, it's at 1. So that's what's happening. It's a very cool diagram. All right, now, sorry, back to where I was. So we can't have the origin. So here we go. Look at that. Beautiful. All right, so we need to figure out some paths that we can approach that line. All right, so we'll do the x-axis again. I mean, it's kind of a classic. So let's go in on the x-axis and see what happens. So path 1 is the x-axis, which is y equals 0. So then we substitute 0 in here, and we end up with the limit as x goes to 0, because there won't be a y anymore, 3x times 0 squared over x squared plus 0 to the 4th, which that whole numerator, that's the limit as x goes to 0 of 0 over x squared, which is 0. And again, it's 0 every step of the way, so therefore the limit is 0. It's not really indeterminate because it's not really 0 over 0. It's 0, 0, 0, 0, 0, 0 all the way in. At the exact spot, it's 0 over 0, but that's not a problem for us. Okay, what about path 2? Let's do it in pink. And I'm going to approach from, I can tell right away, I'm going to skip the y-axis because it's got the same problem as the one above, right? See how it was 4xy and it made 0 and 0, right? 0 over this turns into 0, right? So I'm going to have the same problem here. I'll have 0 in that numerator, and again, it'll be 0 over y to some power, and it's 0. So that's boring. So I'm actually going to try something different. I notice that I've got an x squared and a y to the 4th here, and I think to myself, well, what if I tried x equals y squared, which is a parabola that's sideways, right? So this is a sideways parabola. And I'm doing it because I can tell it's going to make my denominator work out nicer, which I would like, right? So this is the limit, and I'm going to write both of them in because I'm not eliminating right off the bat. Well, I will, but give me a second. Let's think. If I let x be y squared, I take it back. I'm going to let, if I do that, if I get rid of all my x's and put y squareds instead, I'm only going to have y. So I'm going to let y go to 0 of. So you can delay on figuring that out right away and just write the point as it was written in the beginning. But so it's 3 times y squared over y squared squared plus y to the 4th. Right? So wherever there was an x, I put a y squared. In the top, y squared times y squared is y to the 4th. So that's the limit as y goes to 0 of y to the 4th, 3y to the 4th, over, this is y to the 4th plus y to the 4th. So that would be the limit as y goes to 0 of 3y to the 4th over 2y to the 4th. The y to the 4th would go, and we'd be left with 3 halves. Hooray, because that's not 0. So this is a contradiction. And that means that the limit does not exist. But you need all of this work to show it. Let's look at that graph real quickly in Maple. There it is. Isn't that a fun one? So you can see the problem with the axes. They're right there. See that line? That's one of the axes right there. And then there's another one coming along that way. You can see that horizontal line in there. That's one of the other axes. It always takes me a minute to figure out which one's which. But one of them's the x-axis, one of them's the y-axis, and neither one of them's doing you any good, right? So this is the x-axis right there, that fold. So what we did was we came in on the parabola. See the sideways parabola? Right, I'm all turned around, but you get the gist. So the sideways parabola is how we did it. It was actually more like this right there. There you go. That's the sideways parabola that we came on. And you can see that it's 3 halves. It's up high in the sky, as opposed to coming along the x-axis, which is right there, that horizontal ridge line right there. So that's what we're proving. We're proving that the limit doesn't exist because up here it's 3 halves, down there it's 0, and they are not the same number. And you can see it in the graph. There's like a little hole right at the origin. there's a problem.